Okay, today I'm going to talk about Mjøsta rnet and the fire protection strategy of this building. First, I would like to tell a little bit about the Norwegian building codes, so you better understand how this works when we're designing building with wooden constructions. And in Norway, we can choose our building code is performance-based, and we can choose either to do a prospective solutions, that's what we call the easy method, or we can do a full analytical design. If you use the simple method, the prospective solutions in Norway have different requirements of the load-bearing systems according to the building height. So in buildings with 1 to 4 floors, we are permitted using wooden constructions in the load-bearing structures. But buildings with 5 or more floors require non-combustible materials. So that is why in wooden buildings with more than 4 floors, we have to do analytical design. And the Norwegian building code then requires that the main load-bearing system shall be dimensioned in order to maintain satisfactory capacity and stability through a burnout, as it can be modeled. And this is the difficult part when we're working with wooden construction, because the construction will burn itself. And even though the fire burns out in the building, we have to prove that the load-bearing systems not will continue burning and in the end collapse. So that's the difficult part of working with wooden structures. So in Mjøsta rnet, the solution is analytical design. We have to prove that the building maintains stability through a burnout scenario. And we have to increase the fire safety with several design solutions and fire safety technology. Then let's see at the fire protection strategy for Mjøsta rnet. When we work with this building, the main challenges are, of course, the height of the building. This one is 85.4 meters high. So that's a main challenge for us. And we have to prove the load-bearing system will work through a burnout scenario. This building is not allowed to collapse. There is a wooden façade, and this gives a risk of fire spread outside the building, which is a main problem. And of course, hidden fires. A building with combustible materials, there will be a problem with the fire spread in closed areas and things like that. So the main challenges are both the heights and the use of wood in the facade, the load-bearing system, and hidden fires. When construction the Mjøsta rnet, we have dimensioned the load-bearing structures with 120 minutes of fire resistance. And additional, we have proven that this will maintain a complete fire or a total burnout in the building. I'll tell more about that later. All the shafts are closed for each floor with 60 minutes of fire resistance. We don't want any fire to spread from floor to floor through open shafts and sealed areas like that. So every shafts are closed for each floor. Of course, we have sprinkler protection, but in this case, we have increased reliability on the sprinklers. It means double water supply, quick response sprinklers, a lot more water. And in this case, we have also connected the sprinklers to the fire alarm. And this means if someone tries to disconnect any of the sprinklers, you will get a technical alarm on the fire alarm. So you know what's actually happening in the big building. All this is to increase the probability for the sprinkler to control or even extinguish a fire before it even gets a problem for the combustible materials in the building. The next one is the vent hoses in the building. We do some fire protections of them. We don't want any warm metallic hoses to ignite combustible materials. So they are there are insulations materials to protect them. We do not allow any combustible materials in technical rooms or hidden rooms. Everywhere where they can start a fire, or areas where we can't see it, there are only uncombustible surfaces. So we have 2 pressurized stairs to enter the building, or as escape routes. We have, of course, automatic fire alarm, and it's connected directly to the fire brigade, so they will get an early warning. For the fire brigade, there are fire elevator, there are dry risers, and they have their own control room in the building for all the fire installations. This is not common in Norway to use control rooms. I know other countries have this in their regulations. In Norway, we don't normally use that, but we would add this part in the Mjøsta rnet. Then we have the facade, and as I told earlier, it is wooden facade in the building. These are made with elements for each floors, and the cladding is made with the fire retardants, so they will resist the BS1D0. It means difficult to combust, low smoke production, and no burning droplets. We do not allow any combustible insulation materials, however, no plastic materials or things like that, only materials which remain A2S1D0, incombustible materials. Certain areas of the facade are sprinkler protected. This means balconies and the first 2 levels of the building. We want to protect the building against outside fire. And even though the 2 first levels, the facade is made with mainly glass and aluminium constructions, there are some wooden parts, and we protect them with outside sprinklers. We don't want an outside fire threaten the building. And then we have fire stop in the cavities. On this picture, you can see it's 1 element for each floor. And the venting for this element, for the cladding of the element, is separate for every element. And in bottom of the element, there is a fire stop, which reduce the risk of fire spread behind the facade. So all vertical gaps are closed for each floor. And in addition, there are fire stops above the window to further reduce the chance of fire from inside the building to spread up behind the cladding. If you look at a typical floor plan, you can see this picture is a little bit small, but I'll explain. These red lines are the staircases and the elevator shafts. They are made with CLT elements, 60 minutes of fire resistance, and they are all treated with retardants to ensure BS1D0. One of the staircases and all the shafts are covered with non-combustible materials. As I told earlier, these technical rooms and hidden area and one of the stairs, we have covered CLT with plasterboards to reduce the risk of fire spread. The blue lines is the other walls in the floor plan. They are made with traditional non-combustible materials, 60 minutes of fire resistance, but not combustible materials. And a typical floor plan like this, we have an office area, large office area around with the facade. And we have one fire cell for technical rooms, separate fire cells for technical rooms, storage rooms, and shafts and things like that. And we have separate fire cells for the corridor in front of the staircases and the elevator shafts. The same principle is in the part of the building used to hotel rooms, but of course every hotel room is their own fire cell. And in the part with the apartments, every apartment is their own fire cell. But the principles of these main functions is the same in every floor of the building. The yellow marking shows that all shafts are closed for each floor to avoid fire spread from one floor to another. If you look inside the building, we can see a typical compartment where we have these large glulam beams and columns, but the rest of the materials is quite traditional, with plasterboards on the wall. We have concrete with traditional floor materials, and we have sealants with incombustible materials. We can see the same in a picture of the office part. We have these large glulam constructions in wood materials, but the rest of the materials is traditional. So I wanted to say more about the design philosophy behind this building, what kind of testing and research we have done, and how we prove that this wooden construction will resist a complete fire or a total burnout. When we do analytical design with wooden structures, we have to look at what happens to the structure after the fully developed fire. In the decayed period of the fire, will the wooden structure continue to burn, or will the charring stop when the fire inside the building burns out? And the question is, can we use something from the examples below in design, on the pictures below in designing of wooden buildings? The picture in the left shows some trees after a forest fire. In this case, there are a lot of combustible materials. It's outside, so of course there are a lot of oxygen, and there have been a lot of temperature, but still these trees are remaining. Why is that? The picture in the right shows a traditional campfire. And the question is, why are these logs remaining after the fire has burned out? And when we work with these kinds of problems, we want to investigate and better understand, can we use some of these principles in designing safe wooden constructions? So in preparation of the Mjøsta rnet project, we did some testing to learn more about the decay period of the fire. We wanted to study what happens with the wooden structures after the fully developed fire. Will they continue burning, or will the charring of massive wooden structures stop, like you saw on the log campfire on the slide before? So we have tested charring of wooden constructions, and we especially are interested in the decay period of the fire. Not the fully developed fire, but what happens afterward when the fire turns out in the building. What happens with the wooden structures, which are combustible? We have done some tests, and we have made some test columns, which we brought up to a laboratory in Trondheim in Norway. We put them in a test oven, and we used a time temperature curve in 90 minutes before we turned off the burners. 90 minutes is in the Norwegian perspective regulations. There says 90 minutes for a building with more than 4 floors. So that's why we use 90 minutes. But these tests have been done many times before. And normally you take the columns out of the oven, cool them down, and measure the charring depth. What was interesting was the cooling phase. So we left one of the columns inside the oven, where there still was a lot of temperature. We lifted one of the columns out from the oven and put it in room temperature. And for both of the cases, we wanted to investigate what happened in the cooling phase. And we left the fire and charring continue for as much as 5.5 hours before we stopped this test. So normally you stop after 90 minutes. We continued in 330 minutes. We had 3 columns made by Moelven. All of them are 50 times 50 centimeters, and The height of them are 3 meters. And as you can see, we have a lot of temperature sensors mounted inside them, so we can follow the rise of temperature and the charring in the constructions. The column A and B are made to investigate the charring depth and the temperature rise inside the wooden structures. The column C are made to investigate the connections of steel. In Mjøsta rnet is designed in a way that the steel connections are protected with the wood itself. The theory is that a steel construction behind the charring layer will never reach critical temperature for the steel. So we wanted to test one of these connections as well to see what's actually happened. On this slide, you can see a principle for such connections with the steel plates inside the wooden constructions. And to secure these gaps or slices where the steel plate is, they are mounted into mentioned strips to stop the fire to enter the steel. And all the holes for the bolts through the constructions are covered with wooden plugs or fire sealant. The picture on the right, you can see from the test, it still continues burning and charring. Those black lines here are the intermittent strips protecting the steels in the gaps in the wood. And we used the Eurocode's reduced cross-section method in dimensioning these details, but we did a burnout test to actually measure what happens. Here you can see from preparing the test, we have the steel plates inside the columns. We have these intermittent strips protecting them from the openings between the wooden constructions. We have a lot of the temperature sensor inside. And here you can see the bolts holding this together. And the holes I told is, of course, here. All the holes for the bolts are plugged with sealed with wooden plugs. But in this test, we wanted to see what's happened, how effective these plugs is. So on the one side, we sealed with wooden plugs. On the other side, we left unsealed. It means there's an opening in the column to the bolts behind. We have the steel plates here, and these are the bolts through the construction. We have an cemented strip covering this gap, and we have sealed the bolts on this side, unsealed bolts on this side. From the test, we had some interesting results. We can see that all these temperatures are far below what's critical for the steel constructions. And we know that the temperature in the charring layer is 300 degrees. So what's behind will, of course, have lower temperature. But we wanted to investigate if this actually happens. And you can see we have no more than 250 degrees in the steel constructions inside. These lines, you have some stippled lines and some complete lines. The complete ones are those sealed with wooden plugs. The stippled lines are the part not sealed with wooden plugs in their bolt holes. And it's interesting to see there is not a very big difference in temperatures between those two sides. And this is only in the first part of the test. In the second part of the test, the temperatures are pretty the same. We believe this is because when charring, the wood will expand and it will itself seal and insulate the steel behind. When designing Mjøsta rnet, we did protect all the bolt holes with wooden plugs. So this is a safe side solution. But this was an interesting thing we learned with doing this test. That maybe there is not very big difference between those who are sealed and those who are not. This is column B, one of the columns to measure the to investigate the charring depth. And it's 105 minutes into the test. You can see it still burns and charring. And oops, there. And here, this figure shows the measured temperature 40. The yellow line is 40 millimeters inside the columns. The red one is 60 millimeter inside the columns, and the blue line are 90 millimeters inside the columns. The line stops when the charring layer reaches the temperature sensor, because then we no longer can measure the temperature inside the wooden constructions. And we can see that the charring reached 40 millimeter into the columns somewhere between 65 and 70 minutes. It reached 60 millimeter inside the column somewhere between 95 and 110 minutes. And it never reached 90 millimeter inside the columns. We also can see that the maximum temperature, 90 millimeter inside the columns, are around 160, 170 degrees. This is after 180 minutes. And after that, there is a cooling phase and a decrease of temperature in all the structure. Another interesting thing we found in this test, we had one sensor in the middle of the column, and this one never showed more than 40 degrees Celsius during 5.5 hours with fire test. We find that quite interesting, and it shows how well the wooden constructions works as an insulation material in a fire. Okay, when we calculate the charring depth based on the temperature sensor, is this from the column A and B, you can see here. And the green line is calculated charring depth based on Eurocodes with a charring speed of 0.65 millimeters a minute. And of course, we finally measured the actual charring depth of the columns. For column A and B, we got 71 and 74 millimeters, and the actual charring rate was less than according to Eurocode. We can see this as well in our calculations. The one we tested was actually lower than based on the Eurocodes. But we did use these results in designing the columns. We followed the Eurocode as a safe size solution. But the test was arranged to better understand what happens in the decay phase of the fire and to evolve calculation methods for modeling a complete fire in wooden structures. As I said earlier, it's the decay period we are studying in this test. So we use this to involve methods for calculate the cooling phase. Based on the geometry and the type of use in the building, we can and we did calculate the parametric fire curve using Eurocodes for the building. This is just an example, but we did this kind of calculations for different part of Mjøsta rnet. And based on the parametric curve, we then calculate the charring depth and the amount of wood that contribute in the fire. It means the mass of wood contributing in the fire. This mass of wood will of course add up more fire energy. So we calculated the fire energy from these wooden structures and added up the input for the calculation of the parametric fire curve. So we repeated the calculation. We calculated another parametric curve, but this time with more fire energy. When we do this, the charring depth will of course increase and give another energy to the fire. So these processes have to be repeated to investigate whether the fire will stop or if they will continue charring in the wooden constructions. This figure shows such repeated calculations of the parametric fire. The charring depth adds more energy and more temperature for each step. And when we do this kind of calculations, if the calculations converge, like in this figure, this will indicate that the charring will stop. If not, if the curves continues to rise in this figure, the charring will not stop, and we have to reduce the amount of wooden surfaces contributing in the fire. Based on the calculation of the parametric fire curve, and of course including the energy from the wooden constructions, we can calculate the depth of charring. When the amount of wooden surfaces contributing in the fire is small enough, we can find that the depth of charring will stop. In this figure, the blue line shows the calculated depth of charring, this one. You can see it stops up after, in this case, this example, after 40 minutes. And the red line shows the depth of charring based on Eurocode, which continues during time. It's a linear line. If the calculations of the parametric fire curve and the calculations of charring depth shows that the charring continues, we have to reduce the amount of wooden surfaces contributing in the fire. Often we use plasterboards. We cover up the wooden construction with plasterboards, and that means we have no charring behind, we have no pyrolysis zone, and the wooden construction behind is not affected. And this part of the structure will not add up more energy to the fire. So this is how we work with the constructions when we need to reduce the amount of wooden constructions contributing to the fire to end up with something that can resist a complete fire. Then, regarding exposed wood, we learned that large Glulam constructions, like those in Mjøsta rnet, have a huge advantage over CLT in a fire technical analysis. The elements themselves look massive, but the exposed surface is actually quite small compared to walls and or slabs of CLT. Reduced area equals reduced fire load. There are less wooden structures contributing in the fire, and that's of course is huge positive working with fire protection. The ratio of exposed area to volume is also much lower in a Glulam construction compared to a CLT constructions, which gives an inherently larger safety margin for charring. When we work with combustible materials in large buildings, we have to calculate and maybe reduce the amount of wooden surfaces contributing in the fire. And this makes it possible to design a combustible construction which resists a burnout or a complete fire. That's my last slide, and I have to thank you for listening. Please don't hesitate to send me some questions, and you can find my contact information on this last slide. Thank you.